Okay, so thank you very much, and thank you to the organizers for inviting me. So to this very nice conference at this beautiful place. So what I'm going to do is that I'm going to explain some work on some conjectures by Barry Mazur, Carl Rubin, and William Stein on modular symbols. So let me start by sort of briefly recalling what is a modular symbol. So you take a modular form of weight 2 for some group gamma, and let's just say that gamma is most of the time gamma not n, gamma not q, and let's say that q is square free for simplicity. I want to look at a specific map from the rational numbers into C. So what I want to do is that I want to take a rational number R, and then I want to look at what I get if I take my holomorphic cos form of weight 2, and then look at the corresponding 1 differential, and then integrate that from I infinity up to R. And then for some normalization purposes, let me multiply by 2 pi I. Okay? So what I want to do is that I want to say something about the statistics of that map. So for me, that is going to be the modular symbols map. Okay, so we simply sort of have our rational number R, and you can think of this integral as simply just this sort of straight line up to I infinity. Of course, the exact line that you choose doesn't really matter because this is holomorphic, so it's going to be independent of the actual sort of line chosen. Okay. Now, these are important objects in the theory of automorphic functions and automorphic forms. You can use them to compute sort of homology and cohomology of these spaces. But let me sort of say a little bit about what the motivation for Mazur, Rubin, and Stein were. So they were interested in the relation to special values of L functions. So if we write our holomorphic form, write the Fourier coefficient as an, let me normalize it as n to the 1/2, and then e to the 2 pi I and z. And then take a rational number like this one over here, and then look at the corresponding L function twisted with e to the r that I'm going to define now. So this is the sum n from 1 to infinity, an divided by n to the s, and then times e to the nr, and I'm sure you've done that last week also. So e of z is e to the 2 pi I and z, not with an n here, but 2 pi I z. So this is just a standard L function, but with an additive twist. Okay, so there's this additional twist here. So this is a GL2 L function with an additive twist. And it turns out that these admit meromorphic continuation. To all of C, and it's a simple fact, or an exercise if you wish, that if you take this twist of the automorphic L function at the central point, so it turns out that this, at least for some R, has a functional equation, and with the normalization that I took, this is a functional equation of s going to 1 minus s, so the central point is 1/2, and if I denote sort of this thing here, like R in brackets, this is exactly the same. So these numbers, these numbers here are really sort of central values of GL2 L functions with additive twists. Okay? Now, from this, it's easy to verify what's called the Birch-Stevens formula. Which says that if you take a primitive Dirichlet character modulo Q, let me actually say mod M, then if you take the L function with the standard sort of multiplicative twist at 1/2, then that is going to be 1 over the Gauss sum of the conjugate character, and then a sum A in C mod MC star, and then chi of A with the bar, and then these modular symbols A over C. Okay, so there's this relation between the additive twists and the multiplicative twists. And sort of course, it's the theory of Gauss sums that essentially just gives you this directly once you know this result. So the motivation for trying to understand the statistics of this guy was really to try to understand the statistics of these central values. So through the Birch-Swinnerton-Dyer conjecture, this relates to ranks of certain sort of elliptic curves, stuff like that, and that's what Maser and Rubin were looking at, and that led them essentially to try to see what kind of, how does these guys behave on average, say? Excuse me? What is C? C is, of course, M, sorry. Thank you. Okay. Now, so let me state some of the conjectures and results. Let me actually change the notation a little bit. So from now on, let me change slightly and say I take this to be 2 pi I, and then now the real part of the integral from I infinity to R of f of c dc. You can also do the imaginary part, but sort of this turns out to be slightly simpler, only slightly. Okay. So the first conjecture, this is Maser, Rubin, and Stein around 2016. So they conjectured that if you take these modular symbols, now I call them A over C, and I only look at those between 0 and x, and then 1 divided by c. So c is fixed here, and then you look at those a's such that, well, a lies between 0 and x times c. Call this number here gc of x, and x here lies between 0 and 1. So what they conjectured is that when c goes to infinity, this has a limit. And the limit, they call it gx. And they gave a formula for gx. And the formula is that this is 1 divided by 2 pi I, sum n from 1 to infinity, and then the real part of a n times n to the 1/2 times e of nx minus 1, the whole thing divided by n squared. I think I need one of those. Okay, so this over here is a continuous function, and they conjectured that this thing here converges to that. And they had both sort of heuristic sort of evidence and numerical evidence to support this thing. So basically, you have sort of two sums that you need to show that you can interchange them. And if they just assume that they could do that, then they would end up with this conjecture. So the theorem that I proved with Petridis, this is around 2017, is that this conjecture here, let's call it Conjecture One. So Conjecture One is true on average. So what does that mean? Well, it means that if you take your GCs and then you average over C up to M, 1 divided by M, then this thing has the correct limit, G of X, and we even showed that there is like a rate of convergence. There is a positive delta such that it's that limit plus, of course, it's a big O of M to the minus delta. Okay. Now, last year, Diamantis, Hofstein, Kiral, and Lee proved that the conjecture is in fact true, sort of not just on average, but individually. So they proved this result. So Gm of x is G of x plus big O of m to the minus 1/4. So they made this sort of explicit times q to the 1/4 plus epsilon. If you take this, I guess there's an epsilon also here. If you take your f to be a Heck-Kanu form. Okay, and also there's a proof also from last year by Sun and Kim of the same result. Okay, so the conjecture is in fact correct. So both, well, of course, it follows that it's true on average from the individual one, but sort of it's true. Okay, so what is this function? Well, this is essentially the first moment of these modular symbols. So let's move on to the second moment. So if you define EFC to be the full first moment, and over here they're really summing over all A's, but let me now only sum over those A modulo C, such that A and C are co-prime, and then sum over the modular symbols, and then let me divide by the number of them. So that's the Euler-Phi function. So this is the mean. And what I guess this and these things show is that the mean converges to 0. Because if you take x to be 1, then this here is a 0. So this function here is 0. Of course, I have the additional condition that A and C should be co-prime, but you can get around that. So this one is really converging to 0. So we look at the variance of f and c, defined to be the sum A modulo C, A and C co-prime, and then look at A over C minus the mean. This is not so important because asymptotically it's 0 anyway, and then look at the absolute value square, and then again divide by the number of them. So this is the variance. They also made a conjecture for this. So conjecture 2. So conjecture 2, this is Maser and Rubin. So conjecture 2 says that if you fix a divisor of Q, your level, then there should exist a constant CF and DFD such that the variance of FC minus CF times log C converges to DFD as C goes to infinity. So this is the conjecture. So they called this thing the variance shift, no, the variance slope. And they called this thing the variance shift. And they even had a conjecture based on extensive numerics on what the CF should be. So CF should be 6 over pi squared, and then the product of P dividing Q, and then 1 plus P inverse, and then the value of the symmetric square L function at 1, and I'm normalizing my symmetric square L function here in such the way that 1 is at the edge of the critical strip, not the center. So this is the edge of the critical strip. So you can really translate this into to a statement about the Peterson norm of F, if you want to. So this is what they conjectured. This is what we proved. So we proved that this conjecture call it 2, I did, okay. So it's true on average. So what exactly do I mean? Well, what we proved is that if you take the variance, bar FC, and then subtract that constant times the logarithm of C, and then take this thing, and then we multiplied this by phi of C for some technical reasons. Sum this up to m, and then divide this thing here by a sum over C less than m of phi of C, and then C comma Q equals D, and here also C comma Q equals D. And I realize now that I haven't explained exactly what sort of D is over here. So the point is here that you only go, C is only going to infinity over those C such that C comma Q is equal to D. So you fix the component of C that divides Q. So the greatest common divisor of C and Q should be D. So we are taking the average over exactly those. Okay? So what we proved is that this thing here is equal to a constant dfd, and again plus an error term, big O of m to the minus delta. Moreover, we gave a formula for what this is. This is not part of the original conjecture, but we could compute explicitly what is this constant here, dfd. So dfd, it's a slightly complicated sort of formula, but let me just write it anyway to convince you that it is really sort of completely explicit. So it's ADQ times L sim squared of f at 1, and then plus BQL prime of the symmetric squared of f at 1 again. And here BQ is 6 over pi squared product of P dividing Q, 1 plus P inverse inverse, and A dq is the complicated bit, that's BQ times the logarithm of Q divided by D over 2 plus a sum of P dividing Q log P divided by P plus 1, and then plus some absolute constant, which is minus 12 over pi squared, the derivative of the zeta function at 2, and I'm almost done. I just have to subtract log of 2 pi. So it's not necessarily sort of an enlightening constant. As you see, it's completely explicit. At least to the effect that you can sort of compute these guys. So these guys are definitely completely explicit. Okay, and I should mention that sort of as of a couple of weeks ago, there is a different proof of this theorem due to Lee and Sun, using methods very different from the ones that we were using. Okay, so on average, conjecture 2 is true in this way, and I should mention also that there is a theorem due to Blomer, Fuvry, Kowalski, Michel, and Milicevic from 2018 that conjecture 2 holds for D equals 1 if C only goes through primes. So if you restrict yourself to the case of D equals 1 and you only go through C being prime, then they could actually prove this conjecture. Okay. So this is the current status on what we know on the first moment and on the second moment. Of course, you can ask about all the moments. And they made a conjecture that is essentially saying something about all the moments. So let me explain that conjecture. Conjecture 3 says that if you take these modular symbols, divide by the square root of this constant times log C, so this constant here, and in the way that I normalized things this number here is strictly imaginary, so let me divide it by I to become strictly real. So if you look at C in N and N in NC star, then they conjectured that this is distributed according to a standard Gaussian distribution with mean 0 and variance 1. Okay? So the theorem that we proved is that this is true. Okay? So we proved something something slightly sort of stronger than this. So take a D dividing Q. So let D divide Q and look at QD to be those A over C modulo 1 such that A and C are co-prime and C, greatest common divisor of Q, is equal to that divisor D. Then we proved that if you count those R's in QD such that the denominator of that R, so this is a number R here, so C of that R should be less than M, and the modular symbol divided by this normalizing factor CF log C, and I change things to have an I over there, this lying in some interval from A to B, this whole thing here divided by the number of R in QD such that C of R is less than M. This converges indeed to the normal distribution, to pi integral from alpha to beta of e to the minus t squared over 2 dt. And we were even able to sort of make it a little, a small refinement further somehow. So if you take I to be a subinterval of R modulo C with positive measure, then if you only look at those rational numbers that lies in that interval, then this is still true. Okay? So wherever you narrow your focus down and look at rational numbers that lies in any fixed interval between 0 and 1, the modular symbols will exhibit a normal distribution. So that's what we'll prove. So this is the formulation that Maser and Rubin made in 2016. I've seen them later conjecture that it should even be true not for all C of R less than M, but for a fixed C and then just that C going to infinity. And then this would be the average result of that stronger conjecture somehow. So these are the conjectures and these are the results we could sort of prove about them. So let me say a little bit about one extension that one of my students made, and then let me explain a little bit about the proofs afterwards. Now, there's an obvious sort of question that you can maybe ask, namely, is it really sort of essential that that K is 2? So What about higher weight? Now, of course, the modular symbols get placed by a period polynomial in that case. And the period polynomial is a polynomial, so it's not completely clear what the same sort of statements would mean. But anyway, let me explain what my student was able to prove. So if you take an element of a general weight and then write again the Fourier expansion with this normalization, and you write the additive twists in the same way as before, so this is for real part of S bigger than 1. Then again, this admits meromorphic continuation. There's a functional equation, and you can do all these things. We saw, or at least I told you, that it's a fact that when k is equal to 2, the central value of this object is equal to the complex modular symbols. And the theorem, due to Asbjørn-Nordentoft last year, says that whenever you take, say, a square, say alpha beta plus I gamma delta in the complex plane, then if you look at A over C modulo 1, Q dividing C, say, A and C co-prime, C less than M, and then look at, in the general case, these twisted values, additive twists, ER 1/2 divided by square root of CF times log C, whenever this lies in this square in the complex plane, and then divide by the whole thing again. Q dividing C, AC equals 1, C less than M. Then this thing here converges, in fact, to a two-dimensional Gaussian distribution. So e to the minus x squared. Let me write it as c squared over 2, and then dx dy. Okay. So for the central value of these additive twists, the statement is the same. Of course, sort of this also says something slightly stronger than this thing over here, because this is looking at both the real and the imaginary part at the same time, and we only looked at the real part. So this is sort of slightly stronger for k equals 2, but as of yet he hasn't sort of incorporated that you can sort of focus your attention down to any subset of R mod C. Okay. And I haven't told you what CF is in this case, so it's essentially the same, but let me state it now in terms of the Petersen norm. So 4 pi to the k Petersen norm squared divided by k minus 1 factorial, and then the volume of the corresponding quotient h modulo gamma. Okay. Okay, so let me let me say a little bit about the proofs. So the proofs of the three theorems that I stated jointly with Pippich, they are all really sort of specializations of more general statements that holds for any cofinite subgroup of PSL2R. So I stated them just for the Hecke congruence group, but they are really sort of statements that are true for more general sets of groups. I won't reformulate them in this higher generality, but in essence, you just have to sort of replace gamma with a more general group. And then A over C will essentially be the entry A over C in that particular group. Okay. So what we really use as our main tool is a certain Eisenstein series twisted by modular symbols that Dorian Goldfeld introduced back in the early 90s. So it's defined as follows: EKZS is defined to be the sum. So it looks like a standard Eisenstein series, classical Eisenstein series, imaginary part of gamma C to the S, weight 0. But then sort of you multiply by 2 pi I integral from I infinity to gamma I infinity, and then f of C dc to the power k. So this is the definition. It turns out to be convergent for real part of S bigger than 1. Now, on the face of it, this is not such a nice function. So it's not automorphic. But it is something close somehow. So this satisfies a higher order automorphy relation. And let me just sort of state it by an example. So E1 gamma CS minus E1 CS. So if this function had been automorphic of weight 0, this would be 0. It is not. But this guy is automorphic. So this here turns out to be 2 pi I, and then integral from I infinity to gamma I infinity, f of C dc. So this is just a number depending on gamma, and then E set S, the standard Eisenstein series. So if you now take this thing and apply another gamma to this thing, well, this is just a constant, and this one is automorphic. So it's what called automorphic of order 1 instead of order 0 here. So that's the first point. The other point is that this is in fact still an eigenfunction of the automorphic Laplacian, at least formally. So the eigenvalue is S1 minus S, just as for the standard Eisenstein series. That's just a formal computation that you can sit down and do. So even if it's not as nice as the standard Eisenstein series, there is sort of still something that you can do. So it is an eigenfunction, and it turns out also that it has a Fourier expansion. So you can compute a Fourier expansion. So this is phi k s y to the 1 minus s plus some n different from 0 phi k s n square root y k Bessel s minus 1/2 2 pi n y e to the 2 pi I n x. And one can compute these Fourier coefficients just as one can compute Fourier coefficients for the standard Eisenstein series. And what you find is that phi k of s is pi to the 1/2 gamma of s minus 1/2 divided by gamma of s, and then a Dirichlet series that I'm going to denote by LKS00 and phi k Sn. Is that how? Yes, Sn. That's 2 pi to the s, absolute value of n to the s minus 1/2 divided by gamma of s, and then LK Sn. And let me tell you what the Dirichlet series is. Mn. This is the Dirichlet series C from 1 to infinity, C and Q co-prime. And then in the numerator we have A modulo C, and A times D is 1 modulo C. And then you have the modular symbols, A over C to the kth power, and then E M A plus N D divided by C, and then this whole thing divided by C to the 2s, and this turns out to be convergent for real part of s bigger than 1. Okay, so it's a complicated Dirichlet series. But the strategy of the proof really is that we want to understand the analytic continuation and properties of this guy. Once we understand the analytic properties of the Goldfeld-Eisenstein series, we use that to understand the analytic properties of its Fourier coefficients. Once we understand the analytic properties of the Fourier coefficients, we understand the analytic properties of this Dirichlet series, at least in the case where m is 0. And once we understand the analytic properties of this one, and especially the properties around s equals 1, then that will lead, this leads to information about the sum c less than x, a over c to the k, and then e n a over c, where we have a modulo c and a c co-prime. So this is just a standard business. If you know the analytic properties of a Dirichlet series at s equals 1, that allows you to say something about the summatory function of the numerators, which is exactly what this is. And the analytic information that we find for this thing is what allows us to say something about the asymptotic properties of these guys. And this is really what we're proving. We're proving bounds and asymptotics for these sums. And then those properties translate into the theorems that I stated. Okay, so so the question is, how do we then understand the analytic properties of this guy? So let me just spend a couple of minutes concluding to explain how to do that. Now, it turns out that there is sort of an auxiliary series that is nice to look at. We call it dkcs. That is the sum of 2 pi I integral from I infinity, and then not to gamma infinity, but to gamma c, and then f of c dc to the kth power, and then imaginary part of gamma c to the s. So the advantage of doing that is that that one becomes honestly automorphic, right? So this is automorphic. Now, it's no longer an eigenfunction of the Laplacian. It no longer has sort of a nice expansion like this. But the fact is that if we understand the analytic properties of this guy, there's a simple trick you can use to then translate that into properties of this guy. So let me state a proposition, which is really the one that allows us to deduce the analytic properties of this guy. So if you use the automorphic Laplacian plus S1 minus S to this thing, dk zs, then you have an expression for that, which is minus k choose 1, and then L1 dk minus 1 cs minus k choose 2 L2 dk minus 1 cs, and let me just say that this is an explicit differential operator of degree 1. And this thing here is an explicit multiplication operator. Explicit multiplication operator. And now we use this relation to understand the properties of this guy recursively. Because if you then sort of take this identity here and then apply the resolvent, so the resolvent is nothing but the inverse of this thing, then this is a well-studied object, and we know a lot about its analytic properties. Then we can apply that on both sides, and then we get an expression for this thing. And then when k is 1, oh, sorry, this should be a k minus 2 here. And this last term here should only be here, so let me insert here a delta function of k being at least 2, well, at least 1. Yes, at least 1. No, at least 2. So when k is 1, it's only this term. And then this here is just a standard Eisenstein series. And for the standard Eisenstein series, we know all its analytic properties. Then this explicit differential operator doesn't sort of destroy those properties. And then we use the properties of the resolvent. And the properties of the resolvent are well enough understood that we can actually use that to then understand the analytic properties of D1. Okay? Then we understand D1. Then we want to understand D2, so we use this thing again for k equals 2 now. When k is 2, this is the Eisenstein series that we understand. And this is now D1 that I just found a way to understand. And then we use the same technique to understand D2. And then we get sort of a recursion rolling like that. And using that technique, we can understand the analytic properties of this guy for every k. And that's essentially what leads to the analytic properties of these guys. That's essentially what leads to information about these that proves our theorems. And I think I will stop there. No, so this function is automorphic. And in some sense, that's the reason why we moved to this series. So this is automorphic. Which is why we can sort of start using the resolvent. So that's actually an important point. Yeah.
And the Goldfeld-Eisenstein series, do they have a higher rank analogs?
There are higher rank analogs, but we know very, very little about them. As far as so they have been defined, but we don't know if they admit meromorphic continuation or anything like that. We know very little about them.
This has to do with meromorphic continuation of a multiple Dirichlet series?
As far as I know, not directly. Not directly.
Can you tell a little bit more about the trick from going from dk to ek?
From dk to ek, yes. I might have even sort of written it down explicitly. Yes. So here's the formula. It's minus 2 pi I, integral from I infinity to c, f of c dc to the j, dk minus j cs. So there's the formula. Excuse me?
So there in the integration goes from I infinity to what?
To c, not to gamma c, so to c. So the same c is this one.
Ah, okay.
So you see, if I understand all these, then I understand these, because sort of this is clearly sort of holomorphic in all of the upper half length. And there is a similar formula that inverts this. So if you understand the one, you understand the other, and vice versa. This is just a cheap trick, essentially.
Okay, if there are no further questions, let's thank the speaker and all the speakers of the morning session once again.